Today I'm going to make a video on AC induction motor torque curve characteristics, because that'd be the most used motor in the home. And I want to go over it because nobody seems to figure out how to size an AC induction motor properly when they have replaced a gas engine. Some argue it's the same horsepower replacement, some argue that the electric has to be a smaller value. And plus there's this ignorance going around about all electric motors produce the same torque from 0 to some RPM because the Tesla rotor curve has an electric motor in it and this torque curve is flat, but Tesla rotor didn't explain that torque curve, so I'll make a video about that too later on. Okay, so let's start off with the AC induction motor's torque curve. So I'm going to do a little note system so you can pause the video and copy it down. Probably easier way for you to learn than to just listen to my voice over and over and over. Okay, now the proper way to read this kind of curve is as a load torque curve. Electric motor torque curves are never read as a rev torque curve. What I mean is it's not correct to say if I run the speed here, the motor is going to produce max torque here. Okay, it's not how you read the torque curve. On AC induction motor torque curve, this is the startup. This is when you first apply power. You got what's called lock rotor torque. If you notice, it's not that high. It's actually small. There's another misconception about motors. Everybody's saying electric motors develop max torque at 0 RPM, and that's not true. Not true for AC induction motors, at least some of them. So you'll have this particular amount of starting torque. Then you'll have a small dip, and then the torque increases, known to what's called the breakdown torque. And then it falls back down to what's the full load torque when you get like a flywheel, something up to speed, you know. So it's going to have a good acceleration and accelerate really fast, and then come back and finally get to its normal speed if you put a full load on it. If you had no load, it'd just go down to almost synchronous speed. Well, anyways, what this means is at full load, this would be the torque to make a full load and the horsepower at RPM. If you look on the motor's nameplate, because it'll tell you what RPM it makes the horsepower, and then that's where your full load torque could be. And the reason why I want to show this curve is because this point of interest comes in handy in explaining how you can use different horsepower size of an AC induction motor versus a gas powered engine or a diesel engine. This is known as the break-by point, like I said earlier. Now what happens is, as you apply the load, overload the motor beyond the full load torque, the torque will increase on the motor. It'll increase to a maximum called the breakdown. And if your load requires more torque than the breakdown, the torque of the motor will decrease and start to fall off, which means the motor comes to a stall. This ain't like a DC motor. The torque does not increase to max at 0. It has what's called breakdown torque. So remember that. Well, the reason why it's interesting is, if you was to do the horsepower formula, you would notice that the rate of torque increase is much faster than the rate of change of speed when you put a load on it. Like, here's an example right here. I print out a 5 horsepower motor. See? 5 horsepower, and there's the load data curve. The load curve data. 1.0 represents full load. Notice the torque is 7.5 foot-pounds. Notice that if you 1.5 times the torque, it's 11.3. The kind of round is actually 11.25. Well, if you look at the RPM dip from 1.0 to 1.5, you see it's not that significant. In fact, I've done some of the calculations for you. See? 3,501 was the full load speed, and when you overload it by 1.5 times that, so you get 3,433. That results in a speed change of about 2%. And if you do the torque change, you got about a 51% or so torque change, which actually 50%, they rounded. It's 11.25. Well, now if you do the horsepower, which is torque times RPM divided by 5252, as I done here, here's the full load, 4.99, because it's a 5 horsepower motor, and here it is at 1.5 times that amount, 7.38 horsepower, or about 7.4. You can actually get more than that. You can get up 250% with some motors that have 250% breakdown. But what I'm trying to get at here is it holds speed very well, and because of this, you can see the horsepower increases also. Well, so what can we use this for? Well, here's an example of a variable load profile. Say you had a log splitter and it needed 5 horsepower. Notice that it's able to meet the demand up to these points, and then from here the motor will stall. It cannot produce more than 5 horsepower. That's all you get. It doesn't have breakdown torque. It doesn't have the same torque characteristics as an AC induction motor does, so it can't increase its horsepower and torque to such a high magnitude like an AC induction motor can. Well, if it was an AC induction motor that's 5 horsepower, it would be able to meet the demand of 7 horsepower for that small amount it needs. Like for instance, if you go through like I don't know, if you had like a nail or something in a log and it had to break through that and it needed that much horsepower, it can meet the demand, and then the cycle will go back normal again. This is where you can use a 5 horsepower electric motor, AC induction motor, to meet the demand of a log splitter, and you would need like a 7 or 8 horsepower gas engine to do the same, because gas engines cannot increase their torque and their horsepower to such a high magnitude. And so that's how they're able to do that. In fact, there's a rule of thumb, 2/3. Here you go. See? To replace a gas or diesel engine of a variable load profile, use about 2/3 of the gas engine's horsepower rating. Now there's actually a formula if you want to know the exact electric motor horsepower, but it's a little too complex for the general homeowner to understand. You have to know what RMS horsepower is, and it's not really critical because you ain't going to know the load profile unless you had special equipment. But just remember the 2/3 for AC induction motors. Remember that. Use not for all electric motors, AC induction motors. And like, here's some examples of types of variable loads, like hydraulic log splitters, chippers, shredders, saws, air compressors. And here I want to show you what are the standard available horsepower AC induction motors. And I want you to start at 2 horsepower because there's a reason for that. Remember I told you there's different types of electric motors. Well, when you start at 2 horsepower, you get a capacitor start or capacitor run, or you get a capacitor start motor. The reason why that's important is because those are the 2 motors that are the strongest at starting torque, and they have the best breakdown torque characteristics. Anything below that, it's not even worth wasting your time on, because it could be you could be getting a motor that's different. Even though it's AC induction motor, it could be a capacitor, a permanent split capacitor motor which doesn't have a starting switch, or it could be even weaker than that. And those motors really ain't competitive to what you want to have. So I wouldn't go below 2 horsepower for a single phase AC induction motor when you want to convert something over that had gas engines on it. So you want to go they're developed from 2 to 15 horsepower, and the only company I know that makes 15 horsepower for farms at least is Baldor Electric. All the other motor companies I've seen stick with 10 as the most in single phase. And you notice I said best to use on 240 volt circuit, but the nominal is 230. But mine's on the high end. It can vary 10% from 230. It can be like anywhere from 208 to 250 something, but mine measures 240. For y'all's it could be different, but there's a tolerance range that they accept and the motor still will run correctly. Now I want to talk about some applications where you have to be very careful to size the gas engine, the electric motor and the gas engine the same, and here's the reason. Notice over time that 5 horsepower is required over continuous time. There's no dips. What happened is, if you use like a 3 horsepower electric motor and you need 5 continuously, you will burn the motor up. The motor cannot maintain high peak horsepower for long without burning up. It draws too much current. So if you have like a water pump or fan or pressure washer or anything that's continuous rating like that use the gas engine, that like 5 horsepower gas engine, then you must replace it with the same horsepower. You can't use the 2/3 rule of thumb for the electric, where it has to be 2/3 the value of the gas engine. So keep that in mind. If you remember to pause the video and go back, because that made little notes for you if you saw what you can use the 2/3 value for. Okay then. Now I want to talk about how you don't get duped by fake horsepower ratings. Here's the formula for single-phase AC induction motors to find the horsepower on the nameplate. You have the power factor multiplied by the efficiency, multiplied by the voltage, and multiplied by the current, divided by 746. And here, it's a 3 horsepower motor from Leeson Electric. Study it right quick and look at the information. Okay, do you have the information? Good. Now here's the information put on here. Notice that when you do all the calculations, it comes out to about 2.97 horsepower, which the nameplate says 3 horsepower. So this is a true 3 horsepower AC induction motor. See all the information on it? Now one thing you'll notice is it doesn't say SPL or nothing like that, and you want to avoid those motors if it says SPL. The reason why, because it's a marketing junk called special. Then there's nothing special about it other than it's a lie, marketing speak. So if you see a motor that says 5 horsepower SPL, then do not buy that motor. In doing so, you just got yourself ripped off because you didn't get a true 5 horsepower motor. So look out for that. Anything that says SPL, anything like that, don't buy it. Well, I hope my video is educational and helping you understand how the size AC induction motors for loads where gas engines are on them or diesel engines come in handy. Now, before I leave, I want to give you one more piece of information to copy down. So I did some of the calculations for you. Here you go. Keep in mind, this is only for variable type loads. If it's a pressure washer, or anything like that, or a water pump, you have to use the same horsepower or you'll burn the motor up. Also, I want to talk about service factor right quick. All service factor is, if you see SF like 1.15, that means the motor can sustain a 15% increase of overload for horsepower for a long time without being damaged. This motor only has a service factor of 1.0, which this is not bad. It just means that if the bearings on the piece of equipment that I put the motor on start to go out or start to put more force on it, make it harder for the motor to turn, I'm going to have to watch that. But if you have 1.15, you can be a little more lazy on maintaining your equipment